All right, I'm just going to wait another minute. People are still filtering in. For those of you who may not have noticed, the previous lecture, which I apologize again for not being able to present to you live, but I had to travel for a work thing. That lecture covers the sort of extension of collider physics to new subject matter that took place in the 1970s. We talked about the discovery of the tau lepton and the realization of quarks and gluons and the phenomenon of quark confinement in experiments, mostly at the Petra storage ring at DAISY, and the associated experimental techniques. That's uploaded to the agenda page, the Zoom link, as well as the slides. That's lecture 7, so please have a look if you haven't already. I don't think anything in this lecture depends too strongly on what's in there, but it's an important part of the story. The other announcement I wanted to make was about problem set 2, which is posted on the agenda page along with the turn-in link for that. I know you still haven't received problem set 1 back. I'm working on it, and you should receive that back soon. Just going to wait another minute or two to see if anyone else connects, and then we'll launch into lecture 8 here. All right, so today we're going to talk about continued developments in accelerator and detector physics, which are leading up to the birth of more modern-looking experiments. The first use of high-energy proton accelerators and the first proton-antiproton collider, along with its associated detectors, to discover first the 5th quark, which we now know as the bottom quark, in fixed target experiments at Fermilab, which was a brand new institution of the 1970s. We'll talk a little bit about how that came to be. And then I will return to the subject of the weak vector bosons. If you remember from a few lectures ago, when we talked about bubble chamber physics, one of the hot topics of bubble chamber physics towards the end of its reign as a main technique in high energy physics was the observation of weak neutral currents in the Gargamel experiment at CERN. And the discovery of those weak neutral currents was a critical piece of confirmation of the electroweak theory, which was under development in the 60s and 70s. And as we'll see, that theory makes a direct prediction of the mass of the weak vector bosons, and people are going to go and build an accelerator to go out and find them, along with the detectors to be able to make the detection. This is a little bit of a change from what we've seen in previous lectures, where new facilities came online, in most cases without a really clear idea of what would be available at those center of mass energies. We talked about the collider Spear at SLAC and the Mark I detector, which played a critical role in the November Revolution discovery of charmonium and of the tau lepton. Nobody had any idea that either of those states lay at that mass. People had always just profited from building new accelerators and seeing what was there. Now we're going to see a change as the expense of the facilities goes up and the funding climate for high energy physics stops growing as quickly. We'll see a phase change towards people having a more specific idea in mind of what they would like to do with the accelerator before they receive the funding to build it. So what did this standard model look like post-November Revolution? Let's pick 1977 as our date for reasons which will become apparent very soon. A particle physicist working in 1977 would have said that there are 3 generations of leptons: electrons, muons, and taus. Each of them presumably have their associated neutrino, although the tau neutrino has not yet been definitively observed. It's strongly implied to exist based on the leptonic decays available to the tau. The fact that the tau can decay to a muon plus missing energy or to an electron plus missing energy, by analogy with the leptonic decay of the muon, we guess that that is the tau decaying to a tau antineutrino and a neutrino of whatever species of lepton it's decaying into. But that actual direct observation won't happen yet for a few decades. It's a very difficult experiment to do. Still, I don't think anyone in 1977 would have seriously disputed the idea that there's probably a third lepton, a third neutrino in this tau family. We've demonstrated through the observation of jets, first at Spear and then later at the Petra Collider, that quarks and gluons seem to have a physical reality in the sense that they're not just a bookkeeping device for the quantum numbers of hadrons, but they actually can be manifested as hadronic jets. Because of confinement, we don't see the quarks or gluons by themselves, but we can see these highly collimated sprays of particles coming out of sufficiently energetic collisions, talking here about electron-positron collisions at about 30 GeV in the center of mass. That's sufficiently energetic that you see these highly collimated jets, both 2 jet events, which are taken to be quark anti-quark production, as well as 3 jet events, which are taken to be quark anti-quark production with the radiation of a high energy gluon. And in lecture 7, I talked about some of the sort of event shape variables that people use to prove to themselves that that was in fact what was going on. We've had the other part of the November Revolution, besides the discovery of the tau lepton, is the discovery of new hadrons, which are assumed to be bound states of the charm quark, as shown most especially by the discovery of the J-psi particle, but people have also started to do the spectroscopy of D mesons, et cetera, to see the different states that these charm quarks can combine with the other quarks to make. If the quark sector follows the family structure of the lepton sector, then there should probably be a 3rd generation of quarks, as suggested by the existence of the tau lepton. People already give these the name bottom and top, and you'll see in searches from the 1970s, people already starting to search for bottom and top quarks. People have no idea at this time that the top is so heavy. They think it's probably about the mass of the bottom. It will be a surprise how long it takes to actually discover the top quark, but we'll see the bottom quark discovered relatively soon. Finally, the electroweak theory has been written down, and there are predictions for the masses of the bosons that carry the weak force, the so-called W and Z particles. And we'll see in this lecture how people design an accelerator and an experiment specifically to go and find those particles. But to talk about the facilities that are used to make the discoveries of the 5th quark and of the W and Z particles, I want to back up just a little bit and talk about the story of 2 facilities that come online towards in the 1970s, towards the 1980s, which raised the energy of particle beams by basically an order of magnitude relative to what people had been working with up until now. So in the 1960s already, even the early 60s, there was a desire to move past the sort of tens of GeV regime where a lot of experiments had been working at that time. You'll see sometimes people talk about BeV instead of GeV. That stands for billion electron volts, so it means the same thing. Typically, Americans were using this term and Europeans using the term GeV. Soon it will standardize to be GeV everywhere. But if you see a BeV on one of these slides, it just means GeV. So there were facilities that we've already talked about, experiments at the synchrotron at Brookhaven, the AGS, the alternating gradient synchrotron, and the CERN proton synchrotron, the PS, which is still there. These facilities are working sort of at 30 GeV and below, and often in the fixed target mode, meaning that the available center of mass energy is even less. There was convened in the early 60s a joint panel of the Kennedy administration's Scientific Advisory Committee and the so-called General Advisory Committee of the AEC. The AEC is the forerunner to what we now call the Department of Energy, which is ultimately the successor to the Manhattan Engineering District that carried out the Manhattan Project. It was seen that the cost of these new facilities would be too large to just sort of have them organically grow up at pre-existing labs. And so it was understood already at this time that there would have to be a push at the federal level in the US if they wanted to build an accelerator of many hundreds of GeV. And so this joint panel basically solicited proposals from the community for various groups, how they would build a synchrotron in the energy range of 100 to 1000 GeV. You see here the cover of one of the proposals that came out of this effort called a proton synchrotron for 300 GeV by Matthew Sands from Caltech. This is written already in 1960. And there's a sort of charming hand-made plot on the right-hand side here, which shows the central idea that people were thinking about. So up until now, most of these synchrotrons, they had an accelerator in the chain before them. That was often like an accelerator based on static electricity. So you can get up to sort of many MeV of energy by building stages of sort of rubber belts that are using static electricity to charge themselves up. And by putting these things in series with one another, you can get particles up to a sufficient energy. In this case, we're talking about protons up to a sufficient energy where they can then be injected into an accelerator and accelerated up to their final energy. So typically there's one synchrotron that's being fed by one of these like Cockcroft-Walton type accelerators, or there are a couple different technologies that are in use. The main challenge in constructing a very high energy synchrotron, so talking now about the hundreds of GeV range, is the simultaneous need of these types of machines to have a large aperture, meaning that the physical size of the beam pipe where the magnetic and the RF fields are applied has to be large when you're injecting particles at low energy. But in order to get to high energy, you also need a very high field. Once you accelerate up to high energy, you need a high field for steering. And this combination of large aperture and high field is pushing accelerators to be more and more expensive. And that's sort of the reason that they get stuck at this sort of 30 GeV limit for a while. The insight of Sand's report here, and he's not the only person to have thought of this idea. The idea is sort of in the air at the time. Other people, including Robert Wilson, who will hear his name again on the following slides, have the realization that one can solve this problem by building a staged series of synchrotrons. The idea being that one sort of handles the acceleration from a few hundred MeV or 1 GeV up to a few tens of GeV, and then that is the injector to a larger synchrotron, which handles the acceleration from, say, 30 to 300 GeV. Naively, you would think that building two synchrotrons should be more expensive than building one, but it turns out that this is actually not the case. In fact, the reverse is the case, and this has to do with the relationship between energy and aperture. So the reason why you need a large aperture of an accelerator at low energy is that as you accelerate particles, what naturally happens is that the transverse oscillations, so the things that determine the beam size in the transverse plane, get traded off during the acceleration process into longitudinal movements. So as you accelerate a beam, it naturally shrinks in the transverse plane and lengthens its bunch size in the longitudinal plane. Now, the cost of the magnets for the accelerator, which is really the driving thing, sort of goes as the product, let's say, of the field strength and the aperture. It's very expensive to build magnets that can generate a strong field over a large aperture. And one way of thinking about that is just you need to have magnets which surround the beam. And so the larger the aperture, the more material you need, and the higher the current you need going through that larger radius in order to generate the same steering field that the particles feel. So it turns out that this combination of a lower energy synchrotron as an injector and a higher energy synchrotron as your sort of main ring allows you to have low field, high aperture magnets in the first part of the accelerating chain and high field, low aperture magnets in the second half. And this just turns out as an engineering problem to be cheaper. And this sort of unlocks the possibility that these multi-hundred GeV machines can really be achieved. Here you see from that same report some initial estimates of the parameters for this multi-hundred GeV machine, and also an estimate of the costs. Our cost estimates have gotten a little more sophisticated since then, but you see that this thing is coming in at a price of under 100 million. In the end, it's going to cost more because it's built later in time than these initial estimates. But the spirit that you can achieve a good energy for a relatively reasonable cost by factorizing the problem into the so-called booster and the so-called main ring, that idea is going to persist, and that is how Fermilab and the eventual Hadron Collider at CERN that discovers the W and Z bosons will be made. And this is still the case, right? The Tevatron, which was the successor machine at Fermilab, also used a chain of synchrotrons to accelerate the particles, and the LHC at CERN also uses a chain of synchrotrons to accelerate the particles. One reason why this model also tends to work is that if you have a site that already has a lower energy synchrotron, it becomes very useful then as an injector to the higher energy synchrotron. And in fact, because of this relationship between aperture and energy, will lower the cost of that, higher energy machine that you're adding to the end of the chain. There was a meeting at Rochester in 1960 around the time that these proposals were being thrown around. And there was actually some skepticism that such a high energy machine was really needed. You have to remember in 1960, we're talking about before the November Revolution, before the revelation that there are successive generations of matter with higher energies. And there's actually an open question whether or not there's even anything to study at these energies of many hundreds of GeV. Oppenheimer was one of the main proponents. He basically said that while we don't know what we would find at a machine of many hundreds of TeV, he considered it very likely that a novelty would appear. And he said, you know, knowledge of what does in fact occur in this domain will take us a long way towards understanding the nature of matter. This is an argument that we're still having. If you've been following questions about what future facility, for example, could be built at CERN, or what future facility could be built at Fermilab, we find ourselves again in this position where we're a little bit uncertain what the actual physics that this machine would study would be, because we don't actually know what happens at those energies. Unlike the case of the W and Z or the Higgs, there is no good prediction for what the mass of new physics or even the existence of new physics is, and therefore you have to, if you're a proponent of one of these proposals, you have to a little bit take on faith that there will be something higher energy for you to study. There were other camps that were more skeptical. Heisenberg famously advocated against building a 100 TeV scale machine, saying that people had studied cosmic rays up to hundreds of GeV of energy and not really seen any new particles there. And therefore, he considered it likely that there would be really nothing of interest in the multi-hundred TeV regime. But of course, as we discussed way back in the first couple of lectures, the intensity of cosmic rays of those energies is very low. So that left the possibility that there is new physics to study in this regime, but that its cross-section is so small that you will never see it by studying cosmic rays. This turns out to be the correct answer. Robert Wilson, summarizing this meeting at Rochester in 1960, said that the range of opinion between optimism and pessimism is fairly uniformly populated by physicists, but shaded a bit towards those who are optimistically minded. One might argue that you have to be a little bit of an optimist to be interested in basic research at all. In any case, this panel process moves forward. During the early 60s, there are a number of proposals on the table for how one might go ahead and build this next generation machine. The sort of state-of-the-art national labs at this point are Berkeley on the West Coast and Brookhaven on the East Coast. Each of them feel that they are sort of entitled to build the next generation of machine because they already have the people that know how to do it. However, there is like a countervailing desire in the high energy physics community to sort of break the monopoly of the coastal enclaves on energy frontier accelerators. So there is a project called MURA, stands for Midwest University Research Association. And the idea there is that these people want to build a collider in the Midwest specifically because there are universities there, Chicago, Madison, Michigan, Illinois, et cetera. There are all these big like land grant institutions, a lot of them in this area, and they would like to have an accelerator which is more convenient for them to travel to. And this is all tied up with the idea of a truly national lab. Some people, including Leon Lederman, threw around the idea of a TNL. This is sort of a pun on the Brookhaven acronym BNL. The idea is that at Berkeley and at Brookhaven at this time, actually a lot of the beam time which is available is given to local groups, either the staff of the lab itself or to universities in the immediate area. So at like Berkeley, for example, I think about 60% of the experiments are done either by lab staff from Berkeley or from the University of California. And a lot of the remainder is from the universities in the immediate surrounding area. So other universities in California, basically. And so the amount of access that an experimenter, say, at the University of Wisconsin would have to those accelerators, they're working at a huge disadvantage. And so the idea of the truly national laboratory is that this would be a purpose-built new greenfield site, which is specifically to accept proposals for researchers from all over the country and indeed all over the world. And that these should be judged purely on their academic merit and not based on pre-existing arrangements that privilege the people who built the accelerator in the first place. On the other hand, it's reasonable, right, for some people to say, you know, we built this accelerator, our sort of blood, sweat, and tears went into making it work. Why shouldn't we receive priority for the experiments? Anyways, the panel of the US government that's analyzing these proposals sort of picks up this TNL idea. And in fact, before it is named after Fermi, Fermi Lab will originally just be called National Accelerator Laboratory, a reflection of this idea. A second thing that's involved in a new site, besides sort of breaking the monopoly of the traditional powers, is also selecting where that site should be. And this site selection process was kind of a new thing for high energy physics. In the past, labs had always grown up more or less organically around something already existing, whether that be a college campus, as in the case of SLAC, or a military facility, as in the case of the National Laboratory at Los Alamos. Many physicists had a sort of cynical attitude towards the political nature of the selection process. As you can imagine, since there's several $100 million in federal funding that are going to go to some state, there's horse trading that starts to happen. You know, the Johnson administration, which was in power at the time, tried to use the siting of this facility, for example, to twist the arms of state governments to pass fair housing statutes, laws that would prohibit housing discrimination on the subject of race, which was something that the Johnson administration felt was important, but some people thought, you know, it's bad to start mixing up other political aims with the siting of a physics facility, that should be done on a purely scientific basis. Clearly, the Johnson administration did have some input on this process. They, for example, influenced some sites in Texas to be added to a sort of a short list, which hadn't originally been. However, none of those sites were eventually selected, so it's unclear to what extent politics really did influence the final decision. Just to say that Illinois had no fair housing statute when this process began, but they did pass one around the time that the contract for Fermilab was awarded to be sited in Illinois. So maybe it had a positive impact on politics, this site selection process. Robert Wilson, who had been involved in sort of sketching out designs for accelerators and was involved in the discussion about whether a multi-100 GeV collider was really necessary. He was one of Lawrence's grad students from the 1930s, along with many other prominent physicists at the time. He was from Wyoming. He was kind of had an interest in the iconography of the American frontier. That's why like Buffalo were eventually at Fermilab to kind of generate this impression of the American West, even though suburban Illinois isn't really the West. But he also brought that sort of frontier spirit to the technological design of the accelerator. So there was a sort of a risk-taking attitude, an idea of doing more with less, that became sort of the ethos of Fermilab in those early years. Here you see the village of Weston, Illinois in 1966, around the time that the site was decided for Fermilab. And this sort of little village buildings and this barn over here, et cetera, still part of the Fermilab campus. This was basically a failed housing development. So a developer built these houses, but they hadn't been really good at selling them. And they were sort of bailed out by the fact that this land was turned over to Fermilab. There were a few people living here. Some of them were unhappy with the fact that they were getting kicked out of their houses, but on net, this was a huge benefit to the region. Like I said, the ethos of Fermilab in the early days was rather different from labs like Berkeley and Brookhaven, which were the sort of blue buds of high energy physics. They had been doing it since before the war. It's an interesting moment in the funding of high energy physics as well. Through the 40s, 50s, and into the 60s, physicists were very successfully sort of spending down the political capital that they had earned through enabling the Manhattan Project in order to receive ever increasing levels of funding. So the doubling of the funding for high energy physics, that doubling time was much shorter than the doubling time of the overall federal budget. And as a result, basic research was taking up a larger and larger, although still small in absolute terms, share of the federal budget. And there were also other fields which began to be a little bit envious of the amount of attention and funding that high energy physics was receiving. So you see during this debate about the multi-hundred GeV accelerator, sort of for the first time, a dynamic that will recur in debates about later facilities, which is the idea that maybe we should be spending this money on condensed matter physics or biotechnology or something completely different instead. At the same time that the sort of scientific fields are growing apart and squabbling a little more over where the funding for basic research is going, there's just an overall crunch in the federal budget. Part of this has to do with the escalating financial commitments to the Vietnam War. During the 1960s, Congress kept being surprised by higher and higher budget requests to fund the ongoing war in Vietnam. And the Johnson administration was really invested in this Great Society program that was like creating all these new entitlement programs for American citizens, guaranteed health care for the elderly and the poor, et cetera. These also had a negative effect on the amount of budget which was available to high energy physics. So Wilson was really the right man for the time, in the sense that not only did he have this sort of vision of why we needed this accelerator, but he also had a vision that it should be cheap. And that really suited the politics of the age. Compared to CERN, which was already existing at this time and had a reputation for technical excellence, or some might even say perfectionism, the design of the Fermilab complex was more risky and iterative by design. Wilson's idea was that something which worked the first time was therefore over-engineered and could have been built more cheaply. And in fact, in 1971, when the facility was first coming online, there were a number of failures of magnets in the main ring that for a time seemed to throw the project's success into doubt. This ended up costing some money and costing some time. It prevented the lab from opening ahead of schedule. It instead just opened on schedule. And it did come in at a much lower price than, for example, the competing Berkeley design, which would have been more likely to work on the first try, but also much more expensive. So I think given the particular circumstances of the time and the mission that Wilson was tasked to achieve in setting up Fermilab, they really did an excellent job of delivering something which could actually be built given the political constraints of the day. So by 1977, this lab is up and running, has actually been running for several years. And after some initial sort of trial physics runs at lower energies, the proton beam at Fermilab has achieved the heretofore unprecedented energy of 400 GeV. This is not a collider yet, So that 400 GeV beam is available just to do fixed target experiments at this time. And yet, even so, those fixed target experiments are able to access higher mass states than any existing facility. And so one very logical thing you would like to do with this high energy beam is go and look for resonances. Probably the easiest kind of resonance to look for, due to the fact that you can very easily screen out hadrons just using passive shielding, is to look for dimuon resonances. And you see here a picture of the experiment that Lederman et al. Did at Fermilab in 1977. It uses the initial proton beam from Fermilab's accelerator falling onto a target of metal. This metal was alternately copper or platinum. But the actual nuclear target doesn't matter so much, because you're just doing a very simple experiment looking for reactions of the type proton plus target goes to mu plus, mu minus plus anything. And in this case, it's another one of these double arm spectrometer things, which can measure the momentum of the muons with like a 1 or 2% resolution, and doesn't even attempt to cover the full solid angle, and doesn't even attempt to measure the other reaction products. So a relatively straightforward experiment, although you can see it's quite large. This spectrometer is 30 meters from the target to the end of the last muon station. So you're talking about a really big detector physically. And you can see that there's wire chambers in there to help measure the momentum of the particles as they pass through the spectrometer arms. Scintillation counter hodoscopes, which are providing some tracking information in a simple way. A drift chamber, which gives even higher resolution measurement further away here. And some threshold Cherenkov counters, which are performing particle ID, that is to screen out the muons versus any punch through hadrons, which make it through all these layers of shielding. And then each of the arms is symmetric, so it can accept positive and negative muons. So basically, you're looking for the events where two muons are produced, they have the right momentum to enter both of these spectrometer arms at the same time. You look for that coincidence of two well-identified muons, and you measure their momentum and make the invariant mass peak. So a simple experiment in principle. And this is the result that they see. They see a couple of clear resonances here. You can see it in the plots at the left here, where there's sort of peaks on this falling background. And then they also attempt to do like a background subtraction based on a model that has a continuous background with peaks on top of it. And you can see the result there. So we basically have these peaks at just about 10 GeV, and then a second peak, which is a little bit higher. These are, since people are already expecting there to be a third generation of quark, people pretty much immediately recognize this for what it is, which is the bottom quark equivalent of the J psi, which will go on to be called the upsilon, and that the first peak above it there is an excited state of the upsilon, so an upsilon prime, where these two bottom quarks have some additional momentum around each other. So this is a expected discovery, in the sense that the tau had already led us to suspect the existence of a third generation, but it's a pleasing confirmation of this sort of Oppenheimer build it and you will find new physics attitude, because this is a very fundamental discovery which is made fairly early on in the physics program of this new lab, Fermilab, and really seems to validate the concept of using these multi-hundred TeV beams to do physics. Presumably, at this point, people understand that there should also be an even heavier quark, which is the other partner of the bottom quark in the third generation. And this already picks up the name top. And people from this point, which is 1977 forward, will keep doing top searches at all of the energies available to them. Many papers are published over those decades where people are studying there are several false alarms where people think they have evidence for the top. But it ultimately will take until the 1990s, again at Fermilab, for conclusive evidence of the top to be found. But that's a story for another day. The other main discovery of these years is made not at Fermilab, but at CERN, where this idea of the multi-hundred TeV beam is not only adopted, but further extended to produce a proton antiproton collider at these energies. And that is the discovery, of course, of the weak vector bosons W and Z. So just to remind you, the weak theory that Fermi wrote down in the 1930s to try to explain nuclear beta decay has basically gone unchanged for several decades since then. Until the discovery of the neutral current interactions, in fact, people only considered that there were charged current interactions of the weak force. And they tried to look for flavor-changing neutral currents in processes involving, for example, the decay of the kaon. They tried to look for neutral flavor-changing currents, for example, in the final state K plus to pi plus E minus. And they were able to put upper limits on the rate of such decays, but not to actually observe them. So until the 1970s, Fermi's weak model that he had written down kind of isn't really challenged. But there are some theoretical developments during those years that point to the fact that there probably should be weak neutral currents. Weinberg and his co-authors in the late 60s made the prediction that electroweak symmetry breaking, so this theory of how the weak force picks up massive vector bosons as opposed to the electromagnetic force, which has a massless force carrier, the photon. Part of that theory of electroweak symmetry breaking predicts that there should be a neutral weak gauge boson, the Z, which has a mass similar to the mass of the charged current carrier, the W, and it even makes a prediction about what types of neutral current events should happen. There should be, for example, in neutrino beams falling onto a bubble chamber target, both hadronic and leptonic neutral current events. During this time, there's a lot of effort on the theory side to show that the Weinberg theory is renormalizable and can be used to make quantitative predictions in the relevant energy range. The success of that program is considered to be a big evidence in favor that this electroweak theory is actually correct. But the ultimate proof would be to actually go out there and observe these massive vector bosons themselves. And so people begin thinking about how to do that. We've already seen these pictures in a previous lecture, but I'll just flash them again. People did go out and try to detect the two types of neutral current events in interactions of neutrino beams with their detectors. This was actually a very early experiment at Fermilab, E1. So the first experiment to receive this EE designation by Fermilab, which was a fully electronic detector using spark chambers and massive plates of absorber to try to image these two types of neutral current events in neutrino nucleus interactions. You see that there's perhaps some events that fit this characteristic prediction, but this detector doesn't really have the sort of imaging capability to really definitively say whether these are actually the sought for neutral current events or some kind of background arising from like hadronic punch through or some other kind of interaction. And it's eventually only the bubble chamber at CERN, this large bubble chamber Gargamel, which is able to make really convincing pictures of the neutral current events. And they claim the discovery of neutral current events in 1973. You see on this slide examples of both a hadronic events without a muon at the top, where all these different hadrons are produced and then range out. And at the bottom, you see a high energy electron produced by an electron neutrino neutral current event. And then this electron moves through the bubble chamber and produces some little delta rays coming off, which are these curvy things coming off the main track, as well as some secondary electron-positron pairs from the bremsstrahlung. So this is a nice clean picture of a leptonic neutral current event, a nice clean picture of a hadronic neutral current event. And this is considered to be a dramatic confirmation of the electroweak theory. But now we would like to, as I said, go on and actually discover the W and Z particles themselves. So the ratio of charge current to neutral current events in experiments like the one that we just saw can be measured. This measurement estimates one of the free parameters of the electroweak symmetry breaking theory, so-called theta W. This is like the weak mixing angle. And actually, once you have measured or estimated this weak mixing angle, it allows you to predict what the masses of the W and Z particles should be. So ever since Fermi first wrote down his weak theory, there was this weak coupling constant, G Fermi, basically tells you why weak events happen so rarely, and that's because this coupling constant is relatively small relative to, for example, the electromagnetic coupling constant. And in the electroweak theory, there is a simple expression you can write down for mw squared and mz squared, which depends on this G Fermi and on this weak mixing angle, as well as some other constants. And basically, this predicts that the mass of the W should be 80 GeV, and the mass of the Z is 92 GeV. So these particles are almost an order of magnitude heavier than anything else that we've talked about so far. Remember the upsilon that we saw on the previous slide is in the neighborhood of 10 GeV. The CC bar hadrons are below 10 GeV. The tau is below 10 GeV. So you really are needing this order of magnitude leap in energy that the multi-step booster plus main ring type proton synchrotrons can provide in order to have a chance of producing these particles. They're weak particles, and that means that the cross-section is pretty small relative to things that are more strongly produced. And so the game is not just to reach up into the multi-hundred TeV of energy such that you have a chance of producing these, but also to step up the intensity by a lot relative to previous colliders, so that these relatively rare events can be seen. These things have a production cross-section, people knew at the time, on the order of a few nanobarns, which for those of you who are doing physics at CMS sounds like a tremendous cross-section. By modern standards, it is. But none of the accelerator collider experiments that we talked about have either the energy to produce something so massive, nor the intensity to produce it at a rate where you would have any chance of ever actually seeing it. And so a new facility is needed in order to do this. And this facility is known as the SPP bar S. So there was a proton synchrotron of a design not dissimilar to the one at Fermilab, which was built at CERN, called the SPS, the super proton synchrotron, which used the old CERN proton synchrotron dating back from the 1950s as its injector, just in the same way that the Fermilab facility used the booster as the injector to the main ring. The insight that the physicists at CERN had is that you could use this SPP, or you could use this SPS ring, which was pre-existing, extract the beam at one point here in long straight section 6, LSS 6, fire that high momentum proton beam onto a target, use some like analyzing magnets to siphon off the production of antiprotons from those high energy interactions at the target, and then accumulate those antiprotons in a storage ring and re-inject them into the ring, traveling the opposite direction of the protons to make a proton antiproton collider. So people had been doing fixed target experiments at CERN for a few years already using this SPS. The main idea was to extract the beam here at LSS2 and fire it into the north experimental area. We still use this facility at CERN for doing fixed target experiments, including lots of test beams and stuff for CMS, which have been done in this area at Previson. But it turned out that with relatively little expense and relatively quickly, one could build a small storage ring for antiprotons produced over here, and the ability to inject them into the ring traveling the opposite direction. And so this program was approved in 1978, and the first collisions were happening already in 1981, which is sort of a staggeringly fast timescale for things to happen these days. It's worth noting that CERN had already embarked by this point on the construction of the next big collider, LEP, which uses the same tunnel as the LHC, but that's a much longer timescale project. That's going to take about more than 10 years from its initial approval until the first collisions. And so this SPPS project is attractive to CERN, not just because they can largely reuse a facility which has already been built, but because it gives them a sort of program to fill in the gap between the opening of the SPS and the opening of LEP later in the 1980s. So this proton antiproton idea is desirable for a couple of reasons. First of all, if you want to produce the W and Z particles, the main interaction which produces them is to pick out two, in the case of the W, to pick out two valence quarks of opposite flavor, so like U D bar or D U bar pairs. And of course, an antiproton is going to have valence antiquarks in it, where a proton has only valence quarks. So in this energy regime, where it's the valence quark interactions which have the largest cross-section to produce the W, introducing the antiquarks, even though it comes at a cost of the luminosity of the machine and of technical complexity, having to have this extraction, injection, and a separate storage ring to stack the antiprotons, it turns out that the rate of production of W bosons is higher from this arrangement than, for example, just bringing proton beams into collision with one another, where the lack of valence antiquarks really suppresses the available production mechanisms for the W. The main issue here is how to compress the beams to very high spatial densities to bring them into collision. You know, if you're doing a fixed target experiment, your beam is relatively wide. It doesn't matter too much. You know, your target itself is like a macroscopic object. And so as long as the protons are falling onto the target somewhere, you probably don't care too much exactly where, certainly not at a high level of precision where on the target they're falling. But colliding beams is totally different, right? If I want to bring two beams into collision with one another, it behooves me to squeeze down the physical size of the beams as much as possible at the interaction point, because the overall interaction rate is going to be proportional basically to the product of the two beam densities. And so we would like to get that density as high as possible. The way in which that's done is a phenomenon called stochastic cooling, which is so significant in the history of particle accelerators that the Nobel Prize, which will be given out a few years later for the discovery of the particles W and Z, was given not just to Carlo Rubbia, who had the idea for the sort of detector and the overall look of this experiment, but also to Simon Vandermeer, who was the accelerator scientist at CERN, responsible for implementing this technique called stochastic cooling. So what does stochastic cooling mean? In general, up until this point, the sort of theory of steering and focusing of beams was dominated by the so-called Liouville theorem of classical mechanics. So Liouville's theorem says that if I have some distribution of particles, think of like molecules in a gas or a plasma or something like that, I can draw this phase space diagram. In this case, the diagram is contrasting the position of the particles with their momentum. And as long as the work that's being done on this ensemble of particles is being done by a conservative field, so thinking about accelerator physics, we have electric fields and magnetic fields. Then all I can sort of do is distort this phase space diagram in various ways by creating different, for example, electric potentials as a function of X. I can spread this thing out in the phase space, but the total area that it occupies in phase space is conserved. And so in the past, people had always thought about, you know, using accelerators, for example, that beam optics can trade off one dimension of phase space for another. We talked about, for example, as you move a beam through an accelerator and increase its energy, you can trade off, for example, the transverse oscillations. So the size that this thing takes up in the phase space of like momentum perpendicular to the beam, and you can shrink that at the cost of increasing the longitudinal emittance of the beam, for example. The idea of stochastic cooling is that this is true on average for an ensemble of particles, but what this picture misses is that this phase space is not populated by an infinite number of infinitesimal things, but by a finite number of discrete particles. And so while one can only distort this phase space envelope by means of conservative fields, what Liouville's theorem doesn't consider is that I can actually move individual particles around inside of this phase space box while maintaining the overall envelope in phase space of the same size. So basically, instead of this picture of a light blue box that I can sort of distort by introducing conservative potential, I can actually consider what happens to individual particles inside of that phase space, and I can try to arrange the beam optics such that specific particles are kicked from one part of the phase space to another, even if the overall shape of the phase space envelope remains the same. And the way that that's done in practice is by having pickups around the beam line, which measure, for example, how many particles are moving at a transverse, have like an oscillation transverse to the beam of a certain size. And then I can use that signal to formulate a kick that I would like to give the particles when they arrive at my kicking magnet later in the ring. So this is a magnet whose intensity can be ramped up and down according to the signal received by this pickup. For example, if I measure that there are large oscillations transverse to the plane at one frequency, I can calculate where the particles in that part of the bunch that are oscillating with that frequency are, and I can arrange a magnetic field to be applied just to that subpopulation of particles when they come to my kicker later down the line to give the particles in that part of the phase space distribution a kick back towards the center of the distribution. So basically to enrich inside of the phase space envelope, to enrich a certain part of it in protons or antiprotons. This is an idea which is basically specific to hadron colliders for two reasons. In an electron-positron machine, these particles are emitting photons all the time as they're being accelerated. We talked about the Bremsstrahlung. That's a limiting factor on electron accelerators. And every time that that photon is emitted, you know, it has some probability to emit photons with like an energy and angular spectrum. But within that distribution, the emission is a random process. And so as electrons are going around the ring, their location in this phase space diagram is always being kind of randomized by the occasional emission of a photon. But the synchrotron radiation also naturally damps oscillations of the beam, right? The more, for example, that an electron is oscillating transverse to the beam, you know, that oscillating process results from forces being applied to it, acceleration happening. And so it's going to emit photons basically proportional to the amount of acceleration that it's receiving. And so that emission of photons will tend, all else being equal, to damp down the motions of the electrons. So electrons sort of cool themselves in that sense by emitting photons, but with a lower limit to how much cooling can be achieved by the randomization that they pick up when these discrete emission events occur. The proton, on the other hand, neither really radiates that much, so therefore it doesn't get its place in the distribution randomized very often, but it also doesn't have this natural self-damping. So contrary to electron beams, where you need to keep putting energy in all the time to keep them moving, the proton beam is much more stable, doesn't require nearly as much acceleration per turn to keep it there. And it has a very long and persistent sort of memory because this emission of Bremsstrahlung photons is extremely rare. And therefore, you know, this pickup and kicker working in concert over time can sort of shape the beam parameters in a way that would be very difficult for an electron accelerator. So this sort of combination of a lack of radiation and a very long lifetime with a persistent memory for the beam parameters enables this stochastic cooling to be a viable technology for a proton-antiproton, or indeed a proton-proton collider. And that's why they've become sort of viable devices for doing high energy physics. So that's on the accelerator side. What is the technique for actually detecting the production of these vector bosons look like? The original idea is to detect the leptonic decays of the W. So the signature here is quite striking. You have a lepton of high momentum. If the W is 80 GeV in mass, then you will see leptons coming out with a transverse momentum up to 40, 50 GeV in the center of mass, which is a quite striking signal. And this electron should then be recoiling against missing energy. There's a neutrino which is emitted in the decay of the W, which is going to be in the rest frame of the W back to back with it. You can't detect this neutrino on an event-to-event basis because you would need a very, very deep detector with sort of light years worth of calorimetry to actually see the neutrino interaction. But what you can do is measure well all the other reaction products, including from the underlying event that is the breakup of the initial state proton and antiproton, and then infer the presence of the neutrino from the momentum imbalance, which its escape from the detector creates. So the idea of Rubia is to create a very hermetic detector. Hermetic meaning it covers as much of the solid angle of 4 pi around the interaction point as possible. In the case of UA1, the detector that Rubia builds at the SPPS, he has the high quality calorimetry and tracking go down to just a few degrees from the beam pipe, which is a design very similar to what we see, for example, in CMS today. And so the sort of big idea here is that by building a high quality tracking calorimetry to surround the whole volume, I can basically build a neutrino detector that is at least as long as the neutrino is sufficiently energetic to be larger than the inherent uncertainty in this energy measurement, which in this case turns out to be about 10 or 15 GeV. So in the case where the electron has 40 GeV of PT in the lab frame, the neutrino should also be carrying 40 GeV of PT back to back with it and the other reaction products. And therefore, if my calorimetry has a resolution better than that, I should be able to see a signal in the missing energy distribution of events containing a high PT electron. Same thing goes for muons, of course. And this sort of ushers in what I like to call the age of calorimetry. These are the first experiments which are sort of built around surrounding the interaction point quality calorimetry. And this is a property which basically all collider experiments since then have had. Calorimetry allows you to do more than to indirectly infer the presence of a neutrino. It also has some other characteristics that make it especially well suited for doing physics at a hadron collider of the type that we just described. First of all, as we said, these are rare processes we're trying to study. That means we need a high luminosity collider. And that means that there's going to be lots of sort of trash in our detector that we have to sort through. The average proton-antiproton interaction at the SPPS is not interesting to the experimenters, just some kind of quark scattering thing that results in a spray of hadrons. And you don't want your very valuable lepton plus missing energy events to get lost in the shuffle of all this sort of hadronic junk that's being produced in the average event. So building colliders of high luminosity using the technique of stochastic pooling, in this case, to shrink down the typical transverse momentum of the particles such that they can be brought into collision in a very small region, means that we will want to trigger our experiment on something. Of course, a lot of the experiments we talked about have had triggers, but the triggering gets more and more important as the luminosity of the accelerator gets larger and as the events that we're studying is rare. Calorimeters are sort of intrinsically fast. We're talking about times for showers to develop on the scale of nanoseconds, which is quite small relative to the typical bunch crossing frequency of these experiments. And it's relatively easy to get a good quality signal from the calorimeter out quickly in order to decide during the available trigger latency whether or not I actually want to read out the event. compared to particle detectors that have like things drifting through gas, which, as we saw a few lectures ago, is a relatively slow process. Typically, these photodetectors are fast and with good time resolution, so they make ideal candidates for triggering. The sort of algorithmic side of triggering is also easier. Largely, what a trigger based on calorimetry looks like is you have a lot of energy in one part of the calorimeter, so it doesn't involve a lot of complex computations of track parameters or anything like that, which would tend to be costly, both in terms of electronic sophistication, but also in terms of time and trigger latency. The push to higher energy also intrinsically favors calorimetry over tracking detectors, for the simple reason that the calorimeter's energy resolution improves as the particles get more energetic, whereas the momentum resolution of a spectrometer for a fixed field grows worse as the particles are more hermetic. In fact, the calorimeter doesn't depend on the presence of a magnetic field at all for its operation. And so the calorimeter can be sited, for example, outside of the magnet coil of the experiment, which is often what you see done, although not in every case. And the depth of the calorimeter that you need to fully contain the showers grows only as the log of the energy, as opposed to, again, a spectrometer where you need to grow the lever arm basically linearly with the momentum of the particles in order to maintain the same performance. The particles that we're interested in doing physics with at these energies, so in the case of SPPS, that was the W and Z particles, but the same could be said of the top, the Higgs, and a lot of our favored models of physics beyond the standard model. Those things all have hadronic decays to jets. So the W actually decays to jets more often than it does to leptons, as does the Z. And therefore, the fact that calorimeters are sensitive to these jets and are able to measure both charged and neutral particles inside jets, whereas a spectrometer can only really measure charged particles, favors a lot the inclusion of high quality calorimetry into these experiments. And finally, just as we saw that the previous generation of experiments would use sort of layers of different gas and liquid Cherenkov detectors in order to be able to separate different species of particles, to give one example, to separate kaons from pions from muons over a specific momentum range. So too do calorimeters play an obvious role in a comprehensive particle ID system, like the particle flow algorithm that we use, for example, in CMS. So whether or not a particle showers in a relatively thin electromagnetic layer of calorimetry or in a thicker, coarser sampling layer of hadronic calorimetry, gives us a lot of information about whether the initial particle was a electron or photon on one hand versus a hadron on the other. And if it doesn't shower at all, even in the hadronic section, but leaves a track in the muon spectrometer, there's a very high probability that it was a muon. So you still see in some collider experiments dedicated particle ID systems. For example, at the LHC, ELISE has a DE-DX-based particle ID system. Some of the B-physics experiments like Babar at SLAC had dedicated Cherenkov ring imaging systems that were able to do particle ID over a wide momentum range. But the typical experiment that I have in mind, like UA1 or CMS, doesn't have a dedicated particle ID system, other than the fact that the combination of tracking calorimetry and a muon spectrometer kind of inherently has this particle ID property. So in all the collider detectors that you're going to see basically from now on, high quality calorimetry is going to play a role. You're no longer going to just see like a station of electromagnetic shower counters somewhere in the experiment, but they're going to grow to always sort of encompass as much of the full solid angle as possible. Measurement of hadronic showers in particular is hard. We talked a little bit many lectures ago about electromagnetic showers, which are simple on both a conceptual level, but also relatively simple to measure well. There's only two types of particles produced in electromagnetic showers: electrons and positrons and photons. Three types, I guess, if you want, but the basic interaction is very simple. Essentially, all of the energy of the initial particle is converted into charged tracks by the end of that showering process. And so as long as your calorimeter is deep enough to fully contain the electromagnetic shower and has enough segmentation or small enough detector channels to reliably separate, one photon per channel from 2 photons per decay of a pi zero or something like that, it's relatively straightforward to do a good job of that measurement. The materials may be expensive, the electronics may be expensive to do well, but the idea is simple. Hadronic showers, on the other hand, are difficult to imagine measuring well, even if you had a perfect detector. And that's because there are many different physics processes happening inside of a hadronic shower, and there's large fluctuations event to event, shower to shower, in the fraction of energy carried by these different processes. So the first and most obvious component of hadronic showers is actually electromagnetic showers. If I have a hadron impinging on a material, it's going to produce a spray of hadrons, which is typically made up of about 40 to 50% neutral pions, right? So whenever I fire a beam of hadrons, or I have hadrons coming out of a collision into my material, neutral pions are just going to be copiously produced. They're one of the lowest available mass states to hadronize. They come from the hadronization of light quarks. They're just going to be a lot of them, and they decay instantaneously to 2 photons, and so they produce a shower which is very much like the shower of an initial state electron or photon. Those parts are easy to measure well, especially if I have a calorimeter with a high sampling fraction. I can measure it just like I do a shower which is initiated by an electron or photon, by basically counting up the total charge track length and relating that back to the energy of the initial particle. Then about 25% is carried by what I call visible hadronic showers. So here you have the case where things like pi zeros, charged pions, which don't immediately decay, are produced in showers of hadrons. And these hadronic showers, while they have a much longer characteristic length and are sort of like lumpier and harder to put back together than electromagnetic showers, that part of the energy is also relatively straightforward to measure. So basically the number of sort of charged pions in these hadronic, visible hadronic parts of the showers. Again, the challenge is just to accurately count the amount of charge track length. Some of that is going to end up going into components like K shorts or whatever, which travel a bit of distance through the material, but they will then decay back to lighter hadrons, and the measurement can sort of just continue as before. And those parts are not such a big problem. But then there are other parts of the energy which are difficult to measure even in principle. So a big fraction of the energy, maybe 20–25%, goes into actually exciting individual nuclei in the material. So you can either have a nucleus which has an excited state which is accessible to it, a close encounter between a gamma or a pion with that nucleus can transfer kinetic energy into the nucleus and cause it to rise up to this excited state. From there, it may decay back down by emitting, for example, a gamma ray photon. Depends on the available energy levels of the particular nuclei that make up your calorimeter. Sometimes, however, the nucleus just breaks apart into multiple fragments. These fragments are highly charged and typically have like on the order of MeV of energy. And so they will range out in the material of the calorimeter very fast. Unless you're very lucky to have this interaction happen right in the sensitive material, it will typically not leave any energy in your like scintillator layers. And because it's so localized, it causes huge fluctuations in the fraction of energy, which is actually measurable event to event. So that's not a very nice process. And finally, we have things like K-longs, which are produced, which are neutral and can fly a long distance before they decay. And even worse, we have neutrinos, which are produced in, for example, decays in flight of pions. These can also be produced in interactions with the nuclear targets in the material. If we have a muon spectrometer behind us, maybe we catch the part that's actual charged muons, but it's basically hopeless to reconstruct these neutrinos, and they may carry a few percent of the energy away, which is difficult to imagine how you could ever recover that energy. So while the typical electromagnetic energy resolution for example, showers initiated by a photon is on the order of a few percent, the best hadronic energy resolutions which real experiments achieve is typically tens of percent. And therefore, so is the resolution on missing energy, that missing energy again being calculated by adding up all the hadronic recoil in the event and summing it together. This is why I said earlier that the ability of the calorimetry to perform as a neutrino detector of a sort is intrinsically limited to neutrinos which are above about 15 GeV of energy in the case of these experiments like UA1, because the total uncertainty on the measurement of the hadronic recoil is difficult to get below that scale. In CMS, that scale would even be a bit higher. And this is something which, again, I'm emphasizing. It's not just because the hadronic calorimeter is poorly made, although it may also be, but because it is difficult, even in principle, to accurately measure hadronic showers. People over the years have thought of various ways to try to fix this problem. One idea is called compensation. The idea behind compensation is that because of all these different processes, different physical processes going on inside your calorimeter, the response of the calorimeter to different types of particles is rather different on average, unless I do something special to try to equalize it. And that process of trying to equalize the response of the calorimeter to different types of particles is known as compensation. So in a simple model here, you have a MIP, minimum ionizing particle, that would be like a muon going through your calorimeter. You can calculate relatively easily what the dEdx of that muon in your active material and or your absorber is. And so you know on average very well how much energy a muon loses going through your detector. And then you can, for example, at a test beam, fire a beam of muons and measure that response. You'll find that this response to muons, unless you have some very noisy calorimeter system, will be very well, very easy to measure and relatively narrow. You then have the electromagnetic component, which again in hadronic showers is related to the fraction of the energy which are carried by pi zeros. But you can model that, for example, in a test beam by firing electrons into your detector. Electrons are easy to produce a well-calibrated beam of because they're charged. And you can use magnets, for example, to make a monochromatic beam of electrons. And so it's easy to calibrate the response of your detector to electrons. And what you'll find is that relative to the energy actually lost by the electron in showering through your material, this peak will be a bit broader than the MIP peak, because there is still some statistical fluctuations in terms of which specific lengths of charge track end up in the active layers versus the absorber, for example. But on average, this response is going to be pretty close to 1 and again, fairly narrow. Then you have this actual non-pi zero hadronic component, which is the part we were just talking about that's really hard to measure. And that thing will not only have a response much less than 1 on average, meaning that the energy that I actually see is much less than the energy that the initial particle carried, but also extremely broad with this typical width of tens of percent. So compensation is the art of designing a calorimeter so that you can move these 3 components, in particular the E and H components, to arrange for their responses to be as close to one another as possible, and also for their responses to be as close to unity as possible, which you can do by playing with the materials that your detector is made of. That affects, for example, the fraction of charge track that ends up in the absorber versus in the active layers. And also by improving the overall sampling fraction. So having like more active material relative to absorber. This will help you to partially undo the problem with hadronic showers, that they're lumpy. So increase the chance that these high density electromagnetic parts of the hadronic shower actually end up in your active material versus in the passive absorber. And then also through some clever some clever additions to the generic calorimeter concept to try to make independent measurements of these components to allow you to make an event-by-event adjustment of what you think the E and H components of your shower were. People used to think that one way to build a hadronic calorimeter which was compensating would be to use a radioactive isotope, for example, uranium, to build the calorimeter. This calorimeter, which I'm showing here from an experiment called Zeus, not sure how much we'll have time to talk about the Hera Collider and its experiments in this course, but this was generally considered to be a very high quality calorimeter, and it was a depleted uranium as an absorber with plastic scintillator interleaved in the hadronic layers. The original idea of the builders was that the choice of depleted uranium would make this component of the energy, which is lost to nuclear spallation events, more visible to the detector. Because the uranium nucleus has this like large energy nuclear mass defect that makes it a suitable fuel for like weapons or for nuclear reactors, that like making your absorber out of uranium would lead to a larger release of visible energy than making it out of steel or something else, which has a lower nuclear mass defect. It turns out that people were wrong about this idea. Actually, you can build a compensating calorimeter without making it out of uranium, and there's obvious drawbacks to using radioactive materials to build your calorimeter, having to do with radio protection, toxicity, etc. In reality, the best way to build a compensating calorimeter is instead to manipulate the hydrogen content of your active material. So typically, if we're talking about plastic layers of scintillator interleaved with metal absorber, different plastics have different ratio of hydrogen to carbon. And hydrogen has kind of a nice property as a detector of hadronic energy, which is that hydrogen nucleus is just a single proton, which means that the momentum transfer from something like a pi zero or a charged pion, or most especially a neutron, which is produced in the shower, to that hydrogen nucleus is rather more efficient than the heavier carbon and oxygen nuclei that make up part of the active material. And so therefore, by choosing plastics that have a higher ratio of hydrogen, you can increase the response of the plastic to the hadronic component of the showers and help move that H peak closer to 1. So this greater efficiency in measuring, especially the neutron component, can be tuned by changing the sampling fraction as well as the amount of hydrogen in the plastic from the available choices in order to equalize as much as possible the response to hadronic showers versus E&M showers. Another idea which you'll hear tossed around is this idea of dual readout. This was a technology which has been considered, for example, in the HL-LHC upgrade of the CMS experiment, though ultimately not adopted. But this is a clever idea that relies on having two different types of active material in the calorimeter. You can imagine making some of your active layers, or in this case, active fibers. It's just a different geometry of a sampling calorimeter to have long fibers going through than to have flat plates of scintillator, but otherwise works in the same way. So quartz fibers do not scintillate, but they are excellent media for producing Cherenkov radiation. Basically, they count the number of high momentum particles going through the quartz, and that's a different measurement than the scintillator, which is giving you basically the amount of energy lost by charged particles traveling through the scintillator is converted into visible light at some ratio. So having these two independent measurements, the amount of Cherenkov radiation produced on one hand gives you one estimate of the total number of particles that are passing through your detector in the shower, and the scintillator gives you another measurement. And the ratio of these two signals turns out to be proportional to the amount of hadronic versus electromagnetic energy that's being deposited. So that means on an event-by-event basis, I can read out the scintillating part and the quartz part independently, use the ratio of signals deposited in each to make an event-by-event calibration of how much energy went into the electromagnetic versus the hadronic parts of the shower, and then correct for this. And I can do this fast because I have independent readout of these two things such that this kind of compensation could be done already online, for example, at the trigger level. This is a very clever idea. It's shown great promise in test beams, and I guess that we will see more collider detectors making use of it in the future. It's been under active R&D for a long time now. Here's an example of that compensation using two types of active media in action. So these are test beam data from this DREAM calorimeter, DREAM dual readout. I forget what the other three letters stand for, but you can see here that independently, the Cherenkov and the scintillator parts of the system each have an energy resolution, which goes from about, let's take the figure of merit from 10 GeV. So it's about 8% at 10 GeV for the Cherenkov component alone, 7% at 10 GeV for the scintillator component alone. So imagine these as basically two independent calorimetry systems occupying the same space. But if I add together the two, signals with a suitable coefficient on each to minimize the overall energy resolution, I can actually beat the performance of each individual calorimeter system and get only about a 5% energy resolution on 10 GeV particles. So this is working really, really nicely to be able to recover some of the heretofore unrecoverable energy, which is lost by your uncertainty on what part of the energy went into electromagnetic versus hadronic parts of the shower. In any case, the UA1 calorimeter was not particularly well compensating, nor did it have a particularly good energy resolution, but it was effective at the job that it was meant to do. This is a picture of the UA1 detector. You see in the top left here, the large central drift chamber, which would take hundreds of individual wire measurements of the particle trajectories on their way through this thing and produce sort of bubble chamber-like photos of the tracks. And then it's surrounded by a calorimeter system. Imagine two big C-shaped half barrels, which clamp around the sides, as well as end cap calorimeters, which come in from the ends. And then the whole thing is surrounded by this square box of muon stations for identifying muons. The emphasis of this experiment was really on a good quality hermetic calorimetry. Here's a cross-sectional view which shows the same things. There was an electromagnetic component of the calorimeter system, which was inside the magnet here. Then there's a magnet. You have these highly segmented with lots of layers hadronic calorimeter, which is like an iron plastic scintillator sandwich outside. And then the whole thing is covered in more drift chambers, which are used for the measurements of muons. And this is sort of the prototypical design for a collider detector, which remains more or less unchanged to this day. Here's a picture of the sister experiment, UA2, which was sort of also designed to catch the W and Z, but without the aid of hermetic calorimetry. This is more of a multi-arm spectrometer approach, but it did have a very good energy resolution, especially for electrons. And so it did play a role in confirming the discovery of the W and Z. So the emphasis here, instead of on hermeticity, was on highly granular calorimetry with a spherical projective geometry, something you don't really see anymore in collider experiments, but they literally tried to surround the interaction point with a sphere of calorimeters. It turns out that that doesn't have tremendous advantage over building a barrel end cap geometry, which is somehow easier to engineer. And it also had some capability for the detection of hadronic jets. So it was able to see, for example, the electrons from W to E nu decay well with a high resolution, and that shape of that distribution, while making some cuts on the amount of hadronic energy, does give you some ability to be sensitive to the W, but it's the UA1 approach, which is really more influential and more used to this day. Here's a candidate event from UA1 of a lepton plus MET. The lepton is this pink track here of high momentum with the arrow pointing to it. And then all these other tracks, in addition to their energy deposits in the calorimeter, are used to infer the presence of the neutrino. You can see how many hits are on individual tracks from this central drift chamber. Those of you who are used to seeing event displays, for example, from CMS, will recognize that we have like an order of magnitude fewer hits on our tracks typically. This produces a really beautiful image of the particle detector in this sort of cool 1980s inspired color scheme. You have here a picture of the variable called transverse mass from the initial paper alleging the observation of the W. The transverse mass is basically the invariant mass of the lepton and the missing energy in the transverse plane. Because we're talking about hadron collisions, we don't actually know the balance of momentum of the initial state quarks in the longitudinal direction, but we do know that there was no initial state momentum in the transverse plane, and therefore it's the energy imbalance in the transverse plane only, which is useful to making this measurement. You can see there's a cluster of events with a transverse mass approaching the limit of 80 GeV, which you would see in the case where the W decay was fully in the transverse plane. And this clustering of events up against the predicted mass of the W was considered to be a very conclusive proof that the W was real and that these experiments were seeing it. They also saw events like this one. Here's a different sort of style of event display where you see, again, the drift chamber in the center, and then these blue lit up sections are the drift chambers in the outer muon detector. Here we see two high PT muons coming out of the event with an invariant mass consistent with the existence of the Z. But the discoveries at UA1 did not stop there. They also discovered the top quark in decays of the W boson. So this is a claim that the W decays into a top and an anti-bottom quark, and that the top quark has a mass in the range of 40 to 45 GeV. They claim that the top quark is therefore discovered in the mass range of 30 to 50 GeV. The only problem is that we now know this process to be impossible. The mass of the top is about 5 times higher than this. The UA1 experiment also claimed evidence for SUSY by seeing events with a jet recoiling against nothing. So evidence of missing energy production, so-called monojet searches. We now guess that what they were actually observing there were events of the type like W to tau nu, where the tau decays hadronically, or Z to nu nu, where the Z is decaying the Z is decaying to invisible energy, and the hadronic recoil against the Z appears to be recoiling against nothing. So you have to remember that these experiments, while they're achieving the level of technical sophistication in terms of hermetic calorimetry and particle identification capability of a sort of modern experiment, that the analysis was a little less well controlled, let's say, than what we're doing now. So whereas CMS and ATLAS have made really no spurious discovery claims of new particles beyond the standard model, there were several high-profile incidents at these colliders in the sort of early days of hadron collider physics, where people's inability to fully appreciate the possible backgrounds led them to make rather aggressive claims of discovery. The reasons why we have such high standards for discovery in the field nowadays have something to do with this profusion of mistaken, let's say, results promulgated by these experiments. In any case, we're out of time for today, so I'm going to stop here. And we might have time for one burning question if there is one. All right, seeing no hands, I will say goodbye for today, and we will return next time, where we'll continue the story of the evolution of large and complex detector systems past the age of the W and Z. Goodbye.
See you next week.
Thank you. Bye. Thanks.